learners, I am Dr. R.B. Malati, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, Bhilai. I welcome you all again to the course Essentials of Surveying Application and Techniques. In today's lecture, we will continue learning tachyometry, working out good number of example problems. We will also learn about the next method of stadium method, that is a mobile head method. Additionally, we will also address common sources of errors such as instrumental, personal and natural factors and their impact on accuracy. The idea here is at the end of the class, you should be able to perform tachyometric survey with good precision. Okay, let us start with an easy example here. I request you to kindly correlate the problem with the figure given here. The problem goes like this. Two observations are taken upon a vertical staff by means of a theodolite. The reduced level of the trunnion axis is 154.3 meter. In the case of first observation, the line of sight is directed to give staff reading of 1 meter and the angle of elevation as 4 degree 58 minutes. In the second observation, the staff reading is 3.5 meter and the angle of elevation is 5 degree 44 minutes. Compute the reduced level of the staff station and its horizontal distance from the instrument. Let us see the solution. First, calculate the horizontal distance from the instrument. We know that h, that is the horizontal distance from the instrument, is given as s by tan alpha 2 minus tan alpha 1. Here s, which is the difference in the staff reading, can be calculated as 3.5 minus 1 is 2.5 meter. The tan alpha 1 is equal to tan 4 degree 58 minutes is approximately 0.0869 and tan alpha 2, which is tan 5 degree 44 minutes, is approximately 0.1004. So, substituting the values, we get h or d is equal to 2.5 divided by tan 5 degree 44 minutes minus tan 4 degree 58 minutes, which is equal to 2.5 divided by 0.134, which gives the value 185.24 meter. That is, d is approximately 185.20 meter. Now, the next part asked in the problem is to calculate the reduced level of the staff station. The reduced level of B is given as RL of trunnion axis plus V minus height of the lower staff station, for which let us calculate the vertical distance V. This V can be calculated by considering alpha 1, which can be easily shown from the figure. So, the formula for V is equal to d tan alpha 1. V is equal to 185.20 into tan 4 degree 58 minutes, which gives the value 16.39 meter. Now, we can calculate the RL of B. RL of B is equal to RL of trunnion axis plus V minus height of the lower staff station, which is equal to 154.30 plus 16.39 minus 1 is equal to 169.39 meter. Summary here is the horizontal distance from the instrument is 185.20 meter and the reduced level of the staff station is equal to 169.39 meter. One thing you have to remember here is the terms trunnion axis, instrument axis and the center line of sight all refers to one and the same, and it can be interchanged with each other also. So, let us move to the next problem. The vertical angles to vands fixed at 1 meter and 3 meter above the foot of the staff held vertically at station Q van plus 3 degree 20 minutes and 6 degree 40 minutes respectively from the instrument station P. If the elevation of the instrument axis at station P is 101.520 meter, calculate the horizontal distance between P and Q and the elevation of the staff station Q. Let us see the solution. First, calculate the horizontal distance between P and Q. We know h, that is the horizontal distance, or also denoted by ds, s by tan alpha 2 minus tan alpha 1. Here s, which is the difference in staff reading, is 3 minus 1 is 2 meter. Therefore, tan alpha 1 is equal to tan 3 degree 20 minutes is equal to 0.0582 and tan alpha 2, which is tan 6 degree 40 minutes is equal to 0.1169. Substituting the value, d is equal to 2 by tan 6 degree 40 minutes minus tan 3 degree 20 minutes is equal to 2 by 0.0586, which gives 34.11 meter. Now, next part asked in the problem is to calculate the elevation of the staff station Q. So, let us calculate the vertical distance for this. This V can be calculated by considering the alpha 1 as clearly seen from the figure. So, the formula for V is equal to d tan alpha 1, which is equal to V is equal to 34.11 into tan 3 degree 20 minutes is equal to 1.99 meter. Therefore, the reduced level of Q is equal to RL of the instrument denoted by RL of HI is equal to 101.20 mentioned in the figure plus V minus height of the lower staff station, which is equal to 101.52 plus 1.99 minus 1 is equal to 102.51 meter. The summary here is the horizontal distance between P and Q is 34.11 meter and the elevation of the staff station Q is equal to 102.51 meter. Okay, moving to the next problem. The vertical angles to vents fixed at 1 meter and 3 meter above the foot of the staff held vertically at station Q were minus 3 degree 20 minutes and minus 6 degree 40 minutes respectively from the instrument station P. If the elevation of the instrument axis at the station P is 101.520 meter, calculate the horizontal distance between P and Q and the elevation of the staff station Q. Let us see the solution. First, calculate the horizontal distance between P and Q. We know that horizontal distance is given by S by tan alpha 2 minus tan alpha 1. Here S, which is the difference in the staff reading, is 3 minus 1 is equal to 2 meter. Tan alpha 1, which is tan 3 degree 20 minutes is equal to 0.0582 and tan alpha 2, which is tan 6 degree 40 minutes is equal to 0.1169. So, substituting the values, we get D is equal to 2 by tan 6 degree 40 minutes minus tan 3 degree 20 minutes is equal to 2 by 0.0586, which is equal to 34.11 meter. Now, moving to the next part of the problem, that is the calculation of the elevation of the staff station Q. So, for which let us calculate the vertical distance. This V can be calculated by considering alpha 2. So, the formula for V is d tan alpha 2, which is equal to 34.11 into 0.1169, which is equal to 3.99 meter. Now, RL of Q is equal to RL of the instrument minus V minus height of the lower staff station, which is equal to 101.520 minus 3.9 minus 1, which is equal to 96.53 meter. Summary here is the horizontal distance between P and Q is 34.11 meter and the elevation of the staff station Q is 96.53 meter. Now, moving to the next problem, a surveyor wishes to obtain the height of his instrument by observing a staff held upon a benchmark which is at a lower level than the instrument. He takes two observations of the staff, the reading being 3.260 meter and 1.090 meter, and the corresponding angles of depression are 9 degree 36 minutes and 10 degree 48 minutes. Calculate the elevation of the instrument if that of the benchmark is 85.658. Let us see the solution. First, we need to calculate the horizontal distance to determine the elevation of the instrument. We know D is equal to S by tan alpha 2 minus tan alpha 1. Here, yes, which is the difference the staff reading is 3.26 minus 1.09 is 2.17 meter. Tan alpha 2, which is tan 10 degree 48 minutes is approximately 0.1908 and tan alpha 1, which is tan 9 degree 36 minutes is 0.1691. Substituting the value, we get D is equal to 2.17 divided by 0.217 is equal to 100.36 meter. Let us now calculate the vertical distance. This V can be calculated by considering the alpha 1. V is equal to 100.36 into 0.1691 is equal to 16.97 meter. We have to determine the elevation of the instrument if that of the benchmark mark is 85.658 as asked the question. So, RL of the instrument is equal to RL of the benchmark plus the height of the upper staff station plus V, which is equal to 85.685 plus 3.26 plus 16.97 is equal to 104.888 meter. Summary here is elevation of the instrument if that of the benchmark is 85.658 is 105.88 meter. Moving to the next problem, in the tangential method of tachyometry, two vanes were fixed 2 meter apart. The lower vane being 0.5 meter above the foot of the staff held vertical at station A. The vertical angles measured were 1 degree 12 minutes and minus 1 degree 30 minutes. Find the horizontal distance of A from the instrument if the height of the line of collimation is 100 meter. Also find the RL of the A. So, let us first mark the alpha values on the figure. Just naked as justification, we can say the figure has alpha 1 as lesser value and alpha 2 as a higher value. So, proceeding the solution for the problem, first let us calculate the horizontal distance A from the instrument, for which we know D is equal to S by tan alpha 2 plus tan alpha 1. Yes, which is the difference in staff reading is 2 meter. Tan alpha 1 is equal to tan 1 degree 30 minutes is equal to 0.02618 approximately, and tan alpha 2, which is tan 1 degree 12 minutes, is approximately 0.02092. Substituting the values, we can get D is equal to 2 by 0.0471, which gives D is equal to 42.43 meter. Now, to find the RL of the A, let us calculate the vertical distance. This V can be calculated by considering the alpha 1. So, the formula of V is equal to D tan alpha 1. V is equal to 42.43 into tan 1 degree 30 minutes, which is equal to 42.43 into 0.02618, which is equal to 1.11 meter. So, the reduced level of A is equal to reduced level of the instrument minus V minus height of the lower staff station. You don't need to by heart the equation, you just have to frame the equation upon the figure that is given to you. That will be easy for you. RL of the A is equal to 100 minus 1.11 minus 0.5, which is equal to 98.39 meter. The summary of the problem is the horizontal distance of A from the instrument is 42.43 meter and the RL of A is 98.39 meter. Moving to the next problem, the vertical angles to the vanes fixed at 1 meter and 3 meter above the foot of the staff held vertically at station Q were plus 3 degree 20 minutes and minus 6 degree 40 minutes respectively from the instrument station P. With this only you can draw the figure for this problem. If the elevation of the instrument axis at station P is 101.520 meter, calculate the horizontal distance between P and Q and the elevation of the staff station Q. Let us see the solution. Yes, for that we need to first calculate the horizontal distance between P and Q, which can be determined from the formula D is equal to S by tan alpha 2 plus tan alpha 1. Here, yes, which is the difference in staff reading is 3 minus 1 is 2 meter and tan alpha 2, which is tan 3 degree 20 minutes, is approximately 0.0584 and tan alpha 1, which is tan 6 degree 40 minutes, is 0.1166. So, substituting the values, we get D is equal to 2 by 0.175 equal to 11.43 meter. To find the elevation of the staff station Q, let us calculate the vertical distance. This V can be calculated by constructing the alpha 1 as clearly seen from the figure. So, the formula of V is equal to D into tan alpha 1. V is equal to 11.43 into tan 6 degree 40 minutes is equal to 11.43 into 0.1166, which is equal to 1.333 meter. So, the reduced level of Q is equal to RL of the instrument minus V minus height of the lower staff station, that is equal to 101.520 minus 1.333 minus 1, which gives the value 99.187 meter. So, summary for this problem is the horizontal distance between P and Q is 11.43 meter and the elevation of the staff station Q is 99.187 meter. Okay, let us conclude the problems and proceed to discuss the next method known as the mobile method. Before we look into this new topic, let us briefly revisit the concepts we covered in our first class on tachyometry. Yes, this tachyometric measurement can be carried out using different systems. The primary systems include the stadia hair system and the tangential system. The stadia hair system can be divided into two methods, that is the fixed hair method and the mobile hair method. The fixed hair method within the stadia hair system involves setting the stadia hair at fixed intervals. This fixed hair method can be used effectively even when horizontal sights are not possible. And for inclined sights, accurate readings can be obtained by holding the staff either vertically or perpendicular to the line of sight. This method is considered the most common form of tachymetry and is frequently referred to simply as the stadia hair method. In contrast, the mobile hair method keeps the intercept on the leveling staff constant while allowing the distance between the stadia hair to vary. Looking a little detail on this, to implement this technique, we use a theodolite equipped with a special diaphragm and a staff featuring two targets placed at a known distance apart. Okay, let us see one by one. In the diaphragm of the theodolite, the central wire is fixed in the plane of the telescope, ensuring stability during measurement. The stadia hairs, on the other hand, can be adjusted vertically using 2 micrometer screws. This movement is carefully controlled and measured by counting the turns of the micrometer screw. Each turn, whether full or fractional, is recorded on a graduated scale and a micrometer drum. The total movement of the stadia hair is calculated by summing these micrometer readings. The graduation on the micrometer drums are marked in opposite direction to enhance the precision in measurement. Yes, now considering the staff targets. The type of the staff used depends on the distance being measured. For distance up to 200 meter, an ordinary leveling staff can suffice with full meter readings used to observe a constant intercept. However, for distance exceeding 200 meter, it is necessary to use a staff equipped with two vents or target fixed at a known distance apart. To further enhance the accuracy, a third target is placed at the midpoint between the two targets. This setup ensures that even at higher distance, the measurements remain precise and reliable, making the mobile hair method highly effective for long-range tachymetry. Okay, there we finish the mobile hair method. Now, let us look into the errors and the sources in tachymetry. Errors can significantly impact the accuracy of tachymetric surveys and they often stem from a variety of sources. Instrumental errors are common, including improper spacing of stadia wires, incorrect graduation on the stadia rod, and index errors. These issues can lead to inaccurate reading if not carefully checked and corrected. Additionally, personal errors can occur, such as improper positioning of the stadia rod or incorrect reading due to indistinct graduation, especially during longer sights. Also, carelessness in leveling for vertical angle measurement can also introduce errors, highlighting the importance of attention to detail during the survey process. And also, natural factors are another source of errors that surveyors must contend with. Environmental conditions such as wind and temperature fluctuation can affect the accuracy of observations. For example, strong winds can cause the stadia rod to sway, leading to incorrect readings, while temperature change can alter the refractive index of the hair, affecting the sighting accuracy. These natural factors can be challenging to control, making it essential for surveyors to be aware of and compensate for these potential errors when conducting tachymetric surveys, particularly in outdoor regions. Additionally, mistakes in tachymetry like recording the wrong staff intercept or using an incorrect stadia interval, confusion between the angles of elevation and diffraction can lead to erroneous measurement, particularly in complex terrains. And ensuring the accuracy of tachymetric surveys requires meticulous attention of these details, as even small mistakes can compound, leading to significant errors in the final result. It is therefore important to maintain a high level of vigilance throughout the surveying process. Next, the power and optical precision of the instrument along with the quality of the stadia rods plays a significant role in determining the accuracy. Additionally, the position of the sun and atmospheric conditions such as temperature variation and high winds can further impact the accuracy. The observer's vision, the length of the sight, and the inclination of line of collimation are also important factors. The main factor affecting accuracy is probably the length of sight, since for long sights the graduations become indistinct. The error in reading the rod is accidental, therefore, it will not be directly proportional to the length of the transverse, but the errors tend to compensate and reduces as the length of the survey increases. So when you are working on single short sight, under normal condition for ordinary angles of inclination, the expected error in the horizontal distance may be in the order of 1 in 500, and for vertical distance it should not be more than 0.1 meter. Now, if you are working with long lines where a number of setups are required, the errors will tend to be proportional to the square root of the number of setups. It should always be kept in mind an accuracy of 1 by 3000 to 1 by 10,000 in distance is obtainable for sites up to 120 meter, and the average error in horizontal distance may vary from 1 in 600 to 1 in 850. But the closing error in a stadia transfer should not be greater than 0.055 root p, where p is the perimeter of the transfers, and the error in closure for elevation can vary from 0.08 root k on level ground to 0.25 root k on hilly areas where k is the distance in kilometers. Let us quickly recap the key points about errors, mistakes and accuracy in tachymetry. Errors can come from the instruments like improper spacing of stadia wires, from personal handlings like incorrect rod positioning, or from natural factors like wind. Most errors can be minimized with careful use of the equipment and by limiting sight lengths. Mistakes include recording wrong staff intercepts or mixing up elevation and depression angles. Accuracy depends on the instrument's quality, observer's vision and conditions like weather. Generally, accuracy can range from 1 by 3000 to 1 by 10,000 for distance up to 120 meters, with errors balancing out over longer surveys. Let us close this lecture by summarizing the procedure for conducting the tachyometric survey. The procedure is: first, preparation and planning. Before we even set up an equipment, we need to do a base work. This step is called reconnaissance, which is just a term for checking out the area. We take a good look at the terrain, whether it is hilly, flat or somewhere in between, and decide where we will place our instrument. Next, we pick our tool, that is a tachyometer. This is usually a theodolite, that is a device that measures angle and is equipped with a stadia, diaphragm or special tachymetric lenses. These additions help us measure distance and elevation without having to physically measure the ground. Now, we set up our tachyometer at a known station point, basically a place we are already marked and measured. We make sure it is perfectly leveled and centered right over that point. Next, we do the observation of the stadia reading. Once the instrument is ready, we point its telescope at a staff, a long graduated rod that someone else is holding vertically at the point we want to measure. This staff is like our target and is usually marked in meters or feet, so we can read the measurements clearly. Inside the telescope, there are 3 horizontal lines called the stadia heads. We record the readings on the staff where these lines intersect the upper, middle and the lower lines. The middle reading helps us figure out the height of our line of sight, and the difference between the upper and the lower reading is the key for calculating the distance between us and the staff. Next, at the third point, we do the calculation of horizontal distance and elevation. So, using the stadia readings and some trigonometric formulas, we can calculate the horizontal distance to the staff and the elevation of the point where the staff is located. This step is all about turning our observation into numbers we can use for mapping. So, at step 4, we do the field work. Here, we repeat the process, that is aiming, reading and calculating for multiple points across the area we are surveying. If we need to measure a point that's too far away from our current station, we move the tachyometer to a new station and start the process again. As we go along, we keep a detailed record of everything, that is the reading, vertical angles and the positions of both the instrument and the staff. Here the reading is a staff reading. This data is like our field diary and it is essential for the next steps. So at step 5, we do the plotting and the calculation. Yes, back at the office or maybe even out in the field, if you are using a surveying software, we will take all that recorded data and start plotting the points on a map. If you are doing this manually, you will be drawing out the area and marking the surveyed point based on your calculation. Another point that you have to remember here is, if there is contour mapping, which is nothing but the one that shows elevation changes across the land, we use the elevation data from one point to draw the contour lines. The outcome of this step, plotting and calculation, is that these lines connect points of the same elevation, giving us a visual representation of the terrain like a topographic map. Lastly, we do the adjustment and checking. Once all the data is plotted, we double check everything. This means we will be comparing the measurement from different instrument stations to ensure that they are consistent. And if we find any discrepancies or errors, we apply the necessary adjustment to correct them. This might involve reworking our calculation or even going back to the field for more measurements. So let us conclude today's lecture here. In today's lecture, we solved problems in tangential method. We examined how trigonometric formulas are applied to find distance. This technique is particularly useful in challenging terrains where direct measurements are not visible or it is not clear to us. Additionally, we discussed on movable hair method and also learned the common sources of errors such as instrumental, personal and natural factors and their impact on accuracy. We also understood the common mistakes and the error estimates of it. We concluded by summarizing the procedure for conducting the tachyometric survey finally. One thing here is, despite these errors, tachyometric survey typically offer an impressive accuracy ranging from 1 in 500 to 1 in 10,000. And understanding these factors helps to ensure precise and reliable survey result. So, that's all for today, and here we finish a lecture on tachyometry. Thank you and happy learning.